All right, legends, welcome to 6.2. 6.2. We've gotten through 6.1. You know what a confidence interval is. You've heard me nerd out about it. And now, of course, it is time to talk about specifically confidence intervals for proportions. And if I'm going to be really specific and name it, because this, of course, is where we do panic, which I'm going to put on the side here. Your introduction to the term panic, or the acronym, I should say, panic. We're going to name it. It is known as the one sample Z interval for proportions. Now, this video is going to be a lot shorter than 6.1 and 6.3 was, and that's in large part thanks to the fact that I got so zealous and excited in 6.1 that I kind of jumped the gun, and I already used the equation for proportions and confidence intervals in that video and solved it for you once to show you how it would function. If you remember, the confidence interval equation for proportions looks a little like this. It's the sample proportion plus or minus the Z critical value. Put that star to denote that it's the critical value, times the square root of p hat times 1 minus p hat over n. Okay, all things square rooted. So we know this to be the case. And not only have we solved this, but I've actually gone into detail in 6.1 already with you about what it is that we are doing with this Z critical value. Remember, the critical value Z is determined by saying, hey, imagine that you didn't just take one sample, right? So we have a sample. This is your sample. Let's say it was 50 people. I don't know. Okay. And of course, this has got a sample proportion because it's a categorical variable that we're looking at. And a certain proportion of people, let's say it's 0.33, favor a particular bill or something. Let me think of something more exciting. Let's say 0.33 is the proportion of people who truly believe TikTok is going away forever. It, of course, did not, as you may have heard in recent news. Some would argue it was even a propaganda scheme, but we will talk about that further in class. But let's say 0.33 is the proportion of people who truly believe in their heart of hearts that TikTok was going to go away forever, no questions asked, in this sample of 50, right? You might remember from 6.1, and I'll keep this very brief because, of course, we went through it already, that the idea of getting this Z critical value is basically assume that we had a sampling distribution of all the possible versions of a random sample of 50 that hits the exact same target demographic, but of course, there's always going to be a certain amount of sampling error, or I should say sample error. Ooh, come to me, pen, there we go. Where sample to sample, the proportion will be off slightly, right? So you could have samples that say 0.31, that say 0.35. You can even have ones that go way lower, that say 0.29 and things of that nature, or much higher, that say like 0.52, right? And all of that variability exists in our imaginary sampling distribution. And what this critical value does is it says, let's take into account a certain percentage of that. Normally it's 95%, but it can vary. And using that certain percentage, we will say, this is how confident I am. I've, created an interval, and then 95% of the possible intervals I might have gotten from a bunch of different versions of randomly sampling 50 people on this issue in the same way would yield the true population proportion of people who believe TikTok was going away forever. Okay, so all of that should make sense, and of course I go into much more detail in 6.1. So let's zoom forward. You should have our 6.2 slides up, and I'm already on slide 6. All of the slides before that go through the homework, which of course you should go through and feel solid on, and we're just going to go through panic. Let's do the elements of panic. Panic is what you will use for your confidence interval to remember what a confidence interval is and how to construct and interpret. So of course, what the question will say is construct and interpret a confidence interval, I should say, for, and then it will say what it is, the specific situation. Part 1, P, and actually, let's pick a different color for this. Let's do green. P, because we all love it. P is, what do? The parameter. It's the true parameter. What's that going to look like? On slide 9, I say it to you. It will start with something like we are estimating the true proportion of, and then I'll give you context, right? In this case, it was the true proportion of teenagers who believe TikTok was going away forever or something, right? The true proportion of blah, 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 blah. Whatever that proportion is, we are estimating it, right? Well done, scholars. All right. So once we've done that, we move on to A, the assumptions. There are, of course, three main assumptions we must make in order to be able to do this. Assumption one is that we are working with an approximately normal distribution. When I say distribution, I mean sampling distribution. So it's going to be the same rules as for determining normality in a sampling distribution of proportions. Why? Because the way that we become this percent confident is we say, hey, imagine in all the universes that could have possibly existed, what is the proportion of people who truly believe a certain thing, right? And looking at all of those potential possibilities, we create sampling intervals for each one of them, confidence intervals, I should say, for each one of them. And we say, I believe a certain percentage of them, depending on how many we pull from the center, 95 being the normal amount, percentage-wise. I believe that 95% of those capture the true population proportion. So it must be normally distributed, otherwise we wouldn't know how to grab the middle 95%. And of course, the way we get our Z critical value is by assuming the distribution is normal and pulling that normal distribution segment out, using it accordingly. So let's take a look at how that will roll. The way we show it's approximately normal if we're messing with proportions, categorical variables, is just sample size times p hat and sample size times 1 minus p hat. Both of these values must be greater than or equal to 10. And all that's saying is the proportion of the number of people in my sample who actually said, yes, I agree, was at least 10 people. And the number of people who said, no, I do not agree, was at least 10 people. We just want a baseline of a certain number of people. Okay, now we can assume normality. What's step two? Well, step two, of course, is independence. Without independence, we end up in a situation where we can't trust that something will actually distribute normally because it could have peaks and troughs and things caused by different variables being dependent on other variables. A good example of this is when I told you that one of the ways in which I determine if my class is cheated is if instead of seeing a singular peak or a single cluster, I see two, and I see a multimodal curve or even just a bimodal curve. That suggests to me that mayhaps some cheating has occurred, right? We don't want that thing. And of course, the depending factor there was people having access to answers. Independence would suggest otherwise a relatively normal distribution. So what do we do for that? Of course, what we do is we take our sample size n and we multiply it by 10 and we just say, is that less than the true population number? Right, the total population. And if it's not directly stated, like if it's something that you just have to assume, because they're like the state of Wisconsin's population or something, and they don't give it to you, just say we must assume that whatever, 10 times my sample is less than the true population of, and then state what that thing is. Beautifully done. Okay, and this says 10n. This doesn't say ion for those of you who are chemistry fans over here. Let me make that n a little smaller to make this a little clearer. Oh, there we go. Beautiful. And then the last thing is it must be random. Otherwise, it won't be representative. We want it to be random so that it's representative. And this is an old idea, but I just want to go over it over and over and over again so that when you see it on a test or whatever, I just want everything from this year to continually flow through your veins. We never lose it. We keep it going. The momentum is with us, right? We want it to be representative. If it's not randomly selected, it could just be all your buddies from the football team or whatever, and that would not be a representative sample. They may be, biased in some particular way or related in some particular way, and that messes with our sampling. Okay, so we've hit our assumptions. If you take a look at slide 11, I go through in detail everything I just said about why we have to do this. Remember, of course, that independence is actually also the only factor needed in order to calculate standard deviation and also standard error. Standard error being, of course, the standard deviation of a sampling distribution. I went over this part in 6.1, but do be aware that in our equation up here, where we calculate and construct a confidence interval, the margin of error, which is this whole thing here, ME, everything after the plus or minus, is constructed of the critical value, which we have to have a normal curve for in a sampling distribution, and then the standard error is what this whole thing is, which you will remember is actually just the standard deviation of a sampling distribution for proportions. So we're just saying this is how many, standard deviations, critical value away from the mean of the sampling distribution of proportions we have to go to grab all of the versions of reality we want to incorporate, right? The bigger the confidence interval value, I should say, the bigger the confidence level. So this is something to state very quickly that we should already know. Confidence level is how confident you are. It's the percentage. And as confidence level goes up, right, the more confident you are, the margin of error widens. And I said this in I should say also that actually what it is the way I should put this is that the confidence interval widens, right? And by extension, right, the margin of error increases, right? We have more possible values that we are more sure of. We're more sure that the needle lies in a bigger stack of hay than that it lies in a smaller stack of hay. Why is that? Well, because of course there are more possible needles to pull from. So the suggestion here is actually it's, the more confident we are, kind of the wider our possible outcomes have to be. We can't be as narrow. Okay, we move on to slide 12, and with slide 12 we hit the N in panic. And the N is just the name, and we're just going to name it. And what are we going to name it? It is a one sample Z interval for a proportion. So you'll say something like, we are creating a one sample for proportion, Beautiful. We move on to slide 13 where we give the interval. And what do we do to give the interval? It is the equation I showed you before, p hat plus or minus critical value times p hat times 1 minus p hat over n. Now, of course, I already solved using this equation in the 6.1 notes, so I won't bore you with solving it once again, but I will tell you how to use the calculator to do this calculation. Please do refer to 6.1 video notes to see me solve a sampling proportion problem, okay? But let's scroll ever forward past slide 13, and let's take a look at everybody's favorite slide 17, which goes through the values you will do. You will go to stat. You will go to tests. Once you're on tests, make sure you click one prop Z int. Okay. Once you're on one prop Z int, it is super, super important to make sure that you go and do X as your number of successes. Right? Not the proportion. We don't put p hat in. We put the number of people that said it. So if the proportion was 30, whatever. Let's say the proportion was 50%, I should say, in a sample of 50. We put 25 for X. We would not put 0.5. Then we have sample size, whatever that is. And then we will set the confidence level. Make sure you put the confidence level as a decimal. It will pre-populate as 0.95 or 95%. You can change it accordingly. And if you can believe it, we really only have two other things to go through. You should read through all the slides to make sure you're comfortable with them. But the two main things left to be able to be comfortable with are as follows. One, power calculations. Which I'm going to solve on the left here. And then the other being, make sure you can do finding the Z critical value. Now, how do we find the Z critical value? I'm going to start on the right here. Because power calculations, power calculations actually require us to find the Z critical value. We can't just plug in to our calculator to do a power calculation, because power calculations in their very nature are solving for sample size. And the way a power calculation will work is we normally have, right, p hat plus or minus critical value, p hat 1 minus p hat over n. We take that And what we do is we say, well, I just want the margin of error. And remember, the margin of error is the plus or minus part. It's everything after the plus or minus. They give you the margin of error, and they say, well, hey, given a margin of error of blah, that I want that, right? How many people am I going to have to sample if I want to hit that margin of error at a certain confidence level? They'll say, what is n? How many people do I have to sample to be this confident with this tight of a margin of error? So let's put that on the back burner for a second. Just being aware that, hey, this one we can't do in the calculator. We can use the calculator to take it apart, but we can't just plug it into the calculator. We have to solve for n. So we have to be able to find the z critical value on our own, not using just plugging in these raw values into everybody's favorite one prop z int. Okay, so here's how you find the critical value. 1, as I have said in 6.1 notes, the critical value is determined by saying, hey, if I want the middle whatever percent, let's do 95% confident. If I want the middle 95% of possible proportions from my sampling distribution of proportions for the one sample I did, these circles all represent different samples of the same size that could have hypothetically been culled. Then basically I want from one negative z-score up to a positive z-score, right? Surrounding the singular mean that we have. And in effect, what I want then is I actually want the percentile that is on the higher end of that middle 95%. So how do I do that? Well, first I do 100 minus the confidence level, which in this case yields 5. Now that 5% is going to be on the left and on the right equally of my normal distribution. So it's actually going to be 2.5% on either side. And you might remember this from class. So if the middle 95% is what we're pulling from, we know 2.5% we're not pulling from is on either side. What we then simply do is we subtract that 2.5% from the 100%, and we get 97.5%. And what that means is the 97.5th percentile is where this z-score sits that we are looking for, right? Put it in yellow. 97.5th percentile. Okay, so we want the 97.5th percentile z-score in order to find our z-critical value for a 95% confidence interval. What do? Well, this part gets easy. We turn this into a decimal, 0.975. Okay, we do invert norm. Why norm? Well, because we're looking at this as a normal distribution. We do area, 0.975. Okay. Then we do our mean as 0 because, of course, we want a z-score, and our standard deviation as 1. And what you will yield, rounded up, is 1.96. Now, it will always be 1.96 as your critical value for 95% confidence intervals. For 90% confidence intervals, I believe it's 1.645. And then it changes for each one. But this is how you find it in case you forget the value, or also if they give you a weird confidence interval, right? So if they give you a confidence level where they're like, oh, find me this to 67% confidence, you'll do the same thing. You'll do 100 minus 67. You'll find that answer. You'll divide that by 2, and you'll subtract what you get from 100 again. Turn that into a decimal, not a percent, and you will plug that into inv norm, with that being the area, and then 0 for the mean, 1 for the standard deviation. Okay, last step. We have our critical value. Let's say I give you a problem. Actually, let me scroll down. Let me see if we have a problem in this. We do. Go to slide 24 with me. This will be our end point, okay? For slide 24, we are now moving over, by the way. We're scooting on over. I'm going to my green pen again. We're scooting on over. We are doing a power calculation. 6.21 is a perfect power calculation. It says exercise 6.13 whatever presents the results of a poll evaluating support for the healthcare public option in 2009, reporting that 52% of independents opposed public healthcare. So we have a p-hat, 52% or 0.52. We want to estimate this number within 1%. Within 1% is the same as plus or minus 0.01 as a margin of error. Okay? 90% confidence we want here. So that means our confidence level is 0.9. And we want to know the sample size n. Well, let's plug everything in. I'm going to be using this equation up here. And actually, let me highlight it for all of us. Okay, and let's get going. I'm going to do it in red. Margin of error, they just said within 1%, so we'll put positive 0.01. Don't do the negative one. You could technically, but it really doesn't matter. I do positive because it's just always the move, right? Either way, of course, we're going to find we're squaring both sides, so it will go away, but I just do positive to save me time. Equals, we know our critical value, do we? No, we don't. I think I said it a moment ago, but let's do it more time. To find our critical value, we would do inv norm, I'm over here on the right. Area, for the area, instead of it being 0.975, because we're doing 90%, I would do 100 minus 90% equals 10. Divide that by 2, because there are two tails. So we're at 5%. 100 minus that 5% yields 95. So we want the 95th percentile, aka 0.95. Okay? If you plug that in, you would do inv norm, area. You can do this on your own as you're doing it alongside me, right? 0.95. Mean is 0. Standard deviation is 1. Should yield an answer of 1.645. Legendary. So we do 1.645 as our critical value times the square root of p hat, 0.52, times 1 minus p hat, which is 0.48. Divided by n, which is what we are solving for. All right, I'm going to walk you through this algebraically for those who struggle with the algebra part of things. I got you covered. Step 1, divide both sides by 1.645. Because we have to do outside the parentheses first. Do that. I do it one step at a time. 0.01 divided by 1.645. I'm getting 0.006 like 08, something like that, equals. The more precise you can be with these, the easier a time you will have. Square root, 0.52, 0.48. Now keep in mind, I know I wrote 0.00608. You do not have to write every single one of these steps when you're doing your solutions. But be aware, if you are going to round, you have to write the step. If you're not going to round, you can put it in your calculator, but you have to keep the raw value because these are going to vary a slight amount for each one. And you need to make sure that you clarify to the readers and to the stats graders, hey, and to me, hey, here's our situation. Here's where I got this from. Okay. We are now going to square this number. So the next part is we're going to square both sides to get rid of the square root that's on the right. So I am going to square this value. And you're going to get a small number. You should get 0.1234 zeros and then 3695, something like that. In your calculator, it'll be 3.695 or whatever, E negative 5, I believe, right? Which is what this number represents, equals 0.52 times 0.48 over n. Now here's the key switch here. I'm going to multiply both sides by n. Why am I doing that? I'm doing it to get n off of the denominator, right? So now I have 0.1234369 n equals 0.52 times 0.48. Then my last step here before I get an answer is I must divide by the thing that is next to n. Cancel everything except for the n. Then you'll just run that calculation. And I'm going to run that calculation again as we speak. It is parentheses 0.52 times 0.48 divided by the answer that we just got on the left side. And I get 6,754.2384, okay? Now this is the most important part. You have your sample size. Remember that these are entire people. These are whole people in these proportions, okay? If you get an answer for a sample size, it's always people that you're sampling, or engines, it's always whole beings that you're sampling. Always round up, always up. In this case, you notice that it's 6.2384. Normally, we wouldn't round that up, we'd round that down. But the answer is, of course, 6,755 people that you would have to interview. Why? Even though 0.2384 is much less than 0.5, you still need to get to that extra person to be absolutely certain you hit a 90% sense of confidence for a margin of error of 1% here. Okay, so n is equal to 6,755. You must show me both the raw answer and what you rounded it to, because that gives me and the graders a chance to give you credit for saying, hey, I knew that I was supposed to round up no matter what. All right, legends, you've done so much. You have seen and run a power calculation using the equation for confidence intervals for proportions. You've learned how to find the critical value using the percentile of confidence that you want to be, or I should say the confidence level you're trying to be, and the percentile you use to find that critical value. You've gone through and used the by hand calculation method for PANIC, which is a new acronym that you now have. What does that acronym stand for? Of course, P for the parameter. We are estimating the true proportion of people. Hopefully you're doing the interpretive dance from class with me. Then you are making your assumptions. Is it approximately normal, independent, random? Then N, you name it. We are creating a one sample Z interval for a proportion. Then, of course, you give me the interval. You give me the interval, what is it? P hat plus or minus the critical value times P hat times 1 minus P hat over N. That whole thing square rooted. Everything except for the confidence level, or confident, critical value, I should say. My goodness, word salad. You know how to do this on the calculator. You know how to do this by hand. You also understand the theory behind all of this, and I am unbearably proud of you. Thank you for going through these notes with me. Hopefully you feel a sense of calm and awareness. Be sure to go through and try the practice problems that lie at the end here. They are very useful and helpful in your pursuit of knowledge. Thank you for being my students. I adore being your teacher. Once again, this is Mr. Mays signing off.